Right, let's do inverse of a 2 by 2 matrix first of all, because that's by far the simplest. Okay. Right, so first of all, a reminder, you can only find an inverse of a square matrix. Okay, an inverse does not exist for a non-square matrix, only a square matrix. Okay, give you another reason why I mentioned my 99% figure earlier, why we always use square matrices. Okay, now if matrix A is given by this, now I've used letters A, B, C, D to represent the elements of matrix A, then the inverse is given by this. Okay, where I'm going to point out the AD minus BC is the determinant of A. And where have you heard that word before? Written like this. Okay, it's the determinant of A. D-E-T-E-R-M-I-N-A-N-T. Okay, determinant of A. Okay. Now, determinant of A, written det A for short, is this. Now, another way of writing determinant A is to use these modulus brackets. Do you remember the work we did on vectors? I don't know if you watched the vectors or not, okay? But I filmed vectors before I filmed all this, okay? And somewhere in there, I can't remember where exactly now, there were determinants. Oh, it's for the cross product, wasn't it? Remember the vector cross product? Yeah, I mentioned determinants in there. Okay. You're probably going to go and watch the video again now and think, oh, I did mention matrices, okay? The determinant of A, or det A for short, can be written like this, okay? And what you do to find the determinant of a 2 by 2 matrix, this is very important, is you do that times that, which is AD, and then you subtract that times that, subtract BC. So there's no proof of that, okay? Maybe in a future video, but not this one, okay? So the determinant of that is this, okay? To find an inverse matrix, what you do is you first of all take the reciprocal of the determinant. Or if you want, you divide the matrix by the determinant. Remember, that's just going to be a scalar. Okay, it's just a scalar value. Okay, it's a number. Those are elements, and so that times that, subtract that times that, just gives you a numerical value. Say 3. Okay, so the first thing you do is you do 1/3 of. And then what you do for your actual matrix is you just swap those two over. So the D there and the A there, and you just times each of those by -1. Okay, again, sorry, no proof of that, maybe in a future video. There's a proof that exists, but time consuming. Okay, you just got to kind of go with it. Okay, so an important note to make really is that for matrix A, you find the inverse by finding the determinant first of all, and then just doing this. Now, question: what if the determinant A is 0? Okay, what if the determinant of A is 0? Okay, because you can quite easily get that. So suppose you've got, say, I don't know, 1, 1, 1, 1. Or 5, 5, 5, 5, or it doesn't have to be the same numbers, okay? But you can conceivably get numbers such that that times that, subtract that times that is 0. Well, clearly, you end up with 1 divided by 0, which is undefined, okay? That means if the determinant of A is 0, then there is no inverse, okay? There's no inverse. There's no inverse matrix, okay, if the determinant is 0, and that can happen sometimes, okay? This is what we call a singular matrix. I like to think it's because the matrix is on its own. If you've got an inverse, it could be paired with an inverse, for example. Okay, it's kind of a sad thing like that, isn't it? There you go. Okay, so a matrix is singular if it's got no inverse. Okay, let's do some simple examples. All right, why not? Yes, let's do some simple examples. Okay, so look, I'm just going to call that, so 2, 3, 1, just make sure I don't get a singular matrix. That would be a good one to start off with, wouldn't it? Okay, so look, I've got matrix A is 2, 3, 1, 4, shall I just leave that there? Yeah, let's just leave that there, just so you don't have to refer to your notes and so on. Okay. Now the first thing you want to do really is to find what the determinant is. I was about to say determine the determinant, that sounds a bit silly, isn't it? Okay. Well, what is the determinant of that? Okay. Well, it's quite easy. You don't have to write this, you know, the modulus brackets all the time. Okay. Determinant A is quite simple. So you've got 2 times 4, which is 8. Subtract 1 times 3. So 8 subtract 3 is 5. Okay. It's usually a good idea to find the determinant first, because then that will tell you whether there's an inverse or not. If the determinant is 0, then you're done. There's no inverse. Okay, so that's why you should work out the determinant first. Okay. So because the inverse does exist, okay, we can write down what it is. Okay, inverse of A must be 1 over 5, and then remember what we do here, just swap those two over. So that's going to be 4, 2, multiply those by -1, so -3, -1 like that. So that's the inverse of A. Okay. Now if you want, you could put the fifth inside, so you've got 4/5, -3/5, -5, 2/5. Okay, but for simplicity, sometimes it's useful to take the scalar out. Okay. Now you can check how the inverse works. Okay. So remember earlier I said it should be the case that if the inverse exists, that A multiplied by the inverse is going to be the identity. In fact, I probably didn't say it quite like that, but that's kind of what this means. Okay. Yeah. So when you've got the inverse, okay, if you multiply it by the original matrix, you should end up with the identity. That's kind of the. Remember I said there's no division with matrices. That's kind of the alternative. Okay, there is an inverse. Okay, such that this times this is equal to the identity. Okay. Let's just check that works then. So it should be the case that in any order now, the order doesn't matter. If I multiply that by that, okay, I should get the identity. Okay, so what I'm going to do is I'm going to just write down that for simplicity. 4, -3, -1. So don't forget that, the 1/5, because that's part of this inverse matrix. Okay. And I'm going to multiply it by that, which is 2, 1, 3, 4. And we're going to see what happens. For simplicity, I'm keeping the 1/5 there. Yeah. Because then I just end up multiplying integers together. Yeah. So we'll get, what's that, 8, and then -3, so that's 5, isn't it? Okay. And then go on to the next. So that's going to be 12, subtract 12, which is 0. Can you see how this is going? Yeah. And then next row, so you get -2 plus 2, which is 0. And then lastly, -3 plus 8, which is 5. And then look, 1/5 of each of those, you can write it as 1, 0, 0, 1, which is the identity matrix. Okay, so that's our way of checking that this indeed is the inverse matrix. Okay, if you want, try it the other way around. If you did that first, multiply by that, you get the same answer. Okay, you should get 1, 0, 0, 1. Okay, so that's that's inverse matrices. Okay, did you want to see another example? Why not? Okay, let's just try another one. Okay, so let's just I don't know. They're very simple. Okay, so 5, -3, -4, 2. I don't know why I filled them out in that order. I just did. Okay. Let's just have a go at that. Okay. Now you don't really need to work out the determinants separately. You can just write down what the inverse is. It's kind of a method you remember, really. Okay. And as long as you remember this, it's quite straightforward. So you've got -12, subtract -8. So that's -12 plus 8. That's -4. So that will be -1/4. Yeah. There you go with that. So -12 plus 8 is -4, so that means -1/4. You always divide by the determinant, okay? And then we'll do this method of swapping those two around. So that will be -3, 5. Multiply those by -1, so that will be 4. And then that will be -2. That's it, done. Okay? There's no work into showing, that's it. Now if you want as extra, I don't know if you're going to do this, you can just check that when you multiply that by that, you get the identity matrix. Okay. Let me just write that down a bit more clearly. Okay, here. So if you do A times the inverse, you will get exactly the same as if you did it the other way around. A inverse times A, and that should give you the identity matrix. Okay. That's going to be a really, really handy and important result for what's coming up next. Right.